close this and let's move up. Perfect. We just need to. These two paradigms represent different philosophies. Reinforcement learning is about trial and error, where an agent learns by exploring and receiving feedback in the form of rewards. Behavior cloning, on the other hand, is about intimation, where an agent learns by simple copying the behavior of an expert. By the end of this tutorial, you will understand not just what reinforcement learning and behavior cloning are, but also how they are used in real world, their strength, their weakness, and maths behind them, and how can we even combine them. So, first thing first, what is essentially an uh, reinforcement learning? So, let's start simple. Imagine teaching a dog to fetch. Every time the dog brings the ball back, you give it a treat. If it runs away, you give it nothing. Over time, dog realize that fetching leads to reward and ignoring doesn't. So this is the essence of reinforcement learning. Now, the core component of reinforcement learning is typically framed as Markov decision process, which I'll explain. We'll come to this graph later. So let's understand first thing is which is called the Markov decision process, or in short form we can say MDP. So it consists of, first is state, which we'll denote as at X, then the action. This is the it represents the situation the agent is in. Action represents the choice the agent can make, and then third is the transition function, which will represent with T the probability of moving to a new state given an action. So we can also represent as P T given A. So now fourth thing is the reward, which will represent as R. Thus the signal, this is a signal that's telling agent how good its action was. And then fifth, we can define policy as pi. So this is the strategy how the agent chooses the action. And then finally, we can say the value function. So this is the estimate of expected long-term reward. The here the goal is to learn a policy pi. We need to learn it such that it maximize the expected cumulative rewards. So what we want to maximize it, the rewards. We need to learn a policy that maximize the reward. So if you see, if we look at the diagram here, the representation is like we have an agent and it interact with the environment by taking some action. For that it gets an reward. So this is what will go on here. So formally, if we see what is happening formally, so the return form from time step is, so from any at any time step we can say the return, we can define it as the sum. We'll assume that it takes an infinite steps of r t plus k plus 1, where this gamma is a discount factor. It can be between 0 to 1, and it tells us how much we care about future rewards compared to the immediate ones. So this is where you can relate this with the learning rate as well, if you know the deep learning. So what is here, the agent wants to find a policy pi that maximize the expectation return. So in terms of the maths, this will be written as, given this state, what is the expected GTS for this state. So this is how we have defined the term that we are referring. The agent wants to find a policy pi that maximize expected return. Now let's define the Q function. So Q function here, then the Q function of pi, you getting the state, performing the action, is the expectation of the reward gt by s of t, which transition to state by taking an action as a. Now, now will this is how the formulation will work. We will be also going into the real world implementation, where we are going to define our own, we build our own network to do this learning. Here, the important thing is to know what is happening. So you just need to ensure that you understand the MDP, Markov decision processes, and from there we can now look at the learning methods. So how do you actually learn? So there are three major families of algorithm. The first one is the value based method. Second one is the policy based. And third one is the actor critic. So here in the value based is the one that we discussed above, is the Q learning, and Q learning usually has this updation rule: state and action will transition from state action, and we can say plus an alpha time plus gamma, maximizing the Q S dash A dash minus the Q state of Sn here. So these are the transitioning states, and it is used in early success, like uh, so uh, the algorithms, once again, like playing an Atari game. So this is where the Q learning would be used, and let's wait it for loading. Now the next one is the policy based methods, where where what our objective is to understand, like, how directly optimizing the policy, for example, and it will be defined as a gradient, let's say j of theta, and expectation theta, let's log theta, action given state, and then q. We will go more deep into this, what these terms mean and their actual meaning. And the the third one is the interesting one, which is called actor critic method, that combines both actor decision and critic evaluation, which is used in advanced robotics. And we are also going to code one of a robotics example where we are going to teach a robot how to pick and place an object from a position to its desired position. So now, what is there is also thing called deep RL. This is what we are also going to do when we add a deep neural network. The reinforcement learning becomes even more powerful, such as deep QNNs, DQN we can also say it. So, like, the if you have also heard of the AlphaGo, which is reinforcement learning plus deep learning, and it has also defeated the world champion, and also the OpenAI DPO PPO, the scalable reinforcement learning for complex tasks. So their applications are in like robotics, walking robot, drones, and game playings like Atari, chess and Go, finance, trading strategy, recommendation system, AI alignment like RLHF for ChatGPT. Now, the second part, which makes it even more interesting, is the behavior cloning, which is called BC. Now, here we have to flip the perspective. Instead of letting the dog figure it out through a trial and error, imagine showing it again and again how to fetch. The dog just intimates you. This is what is behavior cloning. So, the formal definition in terms of mathematics, we can write. So, we collect expert demonstration pairs of state and action, which can be, which formally we can write as, so let's say for data set D, which has this pair state and action, and we can obviously can go in, if n is a large number, that's really good. So we have some finite amount of data set pairing of state and action. We trained a supervised learning model phi theta to minimize the loss function, which is a function of state, and it outputs an action. So this is nothing but, if you know this mean square error, we can also use it. This is nothing but supervised learning on state action data. So there are many algorithms that can be used here. The first one is the naive BC, trained directly from demonstration, and there is also called dagger, dataset aggregation, which is a fixed distribution shift by querying expert when agent deviates. So then there is other BC with deep learning, train a deep neural network on large demonstration of a data set. So this is what we are going to do in the coding section, in the next section. Here the application are self-driving cars that are trained from human driving data, robotics that teaches arms to assemble the object by intimation, and like now here the limitations are also there. So the main limitation is the generalization of problem, because it fails if it encouraged a state that was not in the data set, and we need a large high quality demonstration. No exploration, so I mean it can't adapt to an unseen cases. So here, so what's different between now, we can say, the reinforcement learning and behavior cloning. So so reinforcement learning is pretty straightforward on based on the rewards, where it is behavior cloning is based on the expert data. And does in reinforcement learning we do exploration. Here we don't do such things. And in terms of data efficiency, we can say reinforcement learning is data hungry, and it is a more efficient process if we have few sets of example. And in terms of reinforcement learning, we can say it is a generalizable model. Generalization is easy, and here we can see it is weak. And application could be robotics, finance, games, and here behavior cloning would be driving cars, intimation robotics, imitation, sorry. So the biggest drawback of reinforcement learning, it is slow and unstable, but and behavior cloning, it fails on unseen data, unseen states. So in practice, we often combine both of these approaches. So here we what we do what we are also going to do is the reinforcement learning with demonstration, which is also called the warm start policy with BC, and then refine with reinforcement learning. So it's an inverse reinforcement learning that recover rewards from demonstration, and we can also say it's a human in loop RL that combine the imitation plus exploration. So to summarize, reinforcement learning is about learning from interaction and reward. BC is about imitating an expert. Each has its strength and weakness. The future lies in the hybrid method that combines the best of both. When you look at the modern AI system, from the robot to large language model, you'll see both RL and BC are at work. These methods are not just theory, they are powering the next generation of intelligent machines. So, this is the um, theory that we require to understand what is going to happen in the coding section, because there we will directly deep dive into the coding, and having this prior information is required such that you understand what is happening when we are developing the PC and the RL systems. So let's move to the next section where we'll start doing the coding. So now we are going to do the coding, our first step is the data collection. First, we are going to learn how can we do the dataset collection for behavior cloning. So we are going to use the gymnasium robotics here, and we are going to use one of their robots, which is the task of that robot is to do fetch, pick and place. And this is I'm going to use the version 4 of that because it works perfectly right now. And what we are going to do with the help of Pygame, we are going to send our action into this simulated environment, and from there we are going to record this process, like the picking of the object and placing it on the required position. So first thing, we as an expert, we are going to do this, and we are going to record the state and action, and after that we are going to uh, teach this to a PC policy model, and then the model is going to do the same thing. And then finally we'll close this off with training a reinforcement learning model which will do trial and error and learn it by itself. And once we are done with, then we are going to the hybrid approach. We are going to take the PC clone model that it has learned, and from there we are going to do the warm start and then do the reinforcement learning. So first thing first, let's start with the data collection part. Let me zoom a little bit so that code is visible. So make sure to do the installation pip install gymnasium, and once it is done, you can import gymnasium as gym, and you can also import the gymnasium robotics. This also you'll need to do the installation. Import numpy as numpy because we want to store this data as a numpy array. And then also you can do installation of Pygames, which we are going to use it to send the action to the environment. That's also a pickle, and from datetime import datetime. So now let's define our key action, which is like we are going to map our WASD keys to the movement of plus X, Y, Z direction. So if you see what is it doing, it is doing a movement in X, Y, and Z direction. So let me zoom it a little bit. So you see, we need to map these things such that it reflects in the coordinate systems. So let's define the key mapping, just like in the games we are used to. So let's do that same thing. So this is what we are defining. Let's define a dictionary. So from pygame dot key small w, we'll define it as numpy as a action, numpy array, and here we'll do whenever it says w, you should move x forward. So for x forward, let's define as minus 0.1 comma 0.0 comma 0.0. So what we are doing is we are defining this key coordinate like x comma y comma z. So this happens when you do the uh, key of w. Now let's define the opposite movement, which is the S key. So it should, in this time it should make plus. And now we want to move toward left. So for that we'll define the A key, and because we want to move the left, so it will be 0.0 and it will be minus 0.1. So this is the delta movement we have defined. It's a very small movement and it makes a lot more sense to take our little steps. And so let's paste this KAS T and then plus. Plus means it will go to the right. Now we need to define the up down movement. So for that we are going to map the Z and X key. So when you press Z, it is going to go on the top. So pygame dot key Z. Let's do one thing. Let's copy it. Z defined as minus. By this time you will be able to also get it what I am trying to do here. And X is going down. So let's define it here. Perfect. Now as you can see, we have done the mapping of movement keys. So now let's define a environment initialization function which is going to bring our robotics model here. So let's define init env and we can say gym dot register environment and we can say gymnasium robotics. Now let's create the environment as gym dot make. The name is fetch. That it is available. Let's see. I'm just trying to see the correct value. So it is fetch, pick, and place. And V4. If you're going to use V3 right now, it is going to throw in error. So, but you can also try. If it works for you, that's fine. V4 works for me, so I'm going to stick with that. Render mode is going to be human because we are going to teach this. And max episode steps. Let's give this 5,000 steps. And it is going to return the environment that we need. So once we execute this function, it is going to bring our robots in a Mojoko environment. So make sure that you have installed the Mojoko. For Mac, it's very straightforward. So you can come here, Mojoko, Advanced Physics Simulations, and you can go to download section and then you can download your required binaries based on the Windows, Linux. You just need to download and extract it. So assuming that you have done this step, then we need to define the teleops, which is transporting the operations and the state in via the interactions. So let's define we can pass this as an environment and we can pass this as a file path. So let's every time expert data.pickle and we can define that we also need a sampling frequency, to how frequently you want to collect the data. Let's define every 5 frames, and that's pretty much we need. Then what we can do, we can initialize our pygame. What this is going to load our key mapping, and we need to define the screen. So it is pygame dot display dot set mode, and we can define a 400 cross 400 screen. It doesn't matter, we are just using it to dis we are just using it to map the screen. We are not entering anything in the pygames. For that we are going to do the Mojoko. Let's also set the caption. So Delio fetch and place task. Now the next thing is we need to define a clock, because timing is something that we want to measure. So let's pygame dot tick, I guess. Pygame guess time dot clock, and we can measure the successful episode. This one says 0. Let's also see how many attempts we are taking, and let's also input the OS, because we are going to save the files. So let's define the folder name as output folder is expert demos, and we can make sure that this make directory, this output folder exists. So okay. If it is there, then do nothing, otherwise create it. So now let's set a seed value, so that we should, and now we are debugging, so we should replicate the environment. And once this is done, we can enter into collecting the data. So let's define a convergence criteria as while successful episode is less than 1, which means we have not even collected one successful attempt. So till then keep running, and then we can increment our total attempt. So now we need to call our environment dot reset. What it does, it is going to give us, once we pass the seed value, it is going to give us the replicatable values of observations and information. So this will be useful. Like let's define a flag which will mark as false, which is a done state, and let's count the steps. And in the piece root data, we are going to store the data for episode. Now let's capture initial positions. this is going to be useful when we are training the PC model, and we can initial check position. So there is called achieve goal, and the initial, not the object but the target. Checked desired goal. So what we are interested is the distance between these, the initial and the final desired goal locations. If they are within certain range, then we can say, yeah, we have placed the object exactly there. So, while we have not even collected one episode, and we have marked the as while not done, meaning now we can enter into grabbing the object. Then we can define the action as numpy dot zeros, and with 4, and you can define the t type as y dot float 32. So for event in pygames dot event dot get, let's get all of the event. If let's handle a base case where if an event is an exit event, you need to make sure that there is an exit event that which quits the game. So if pygames dot quit happened, then we can mark the done to be true, or if e dot type is equals to pygame dot key down, and there is a control C. If we press event dot key equals to pygame dot key escape, then we are also going to mark this done to be true, and we can break. Right, so now we can collect the keys that has been pressed by the human. Pygame dot keys dot get pressed. Now we can see which key was got pressed, and according to that what data we need to process. So we can go for key comma data in key action dot items. So if key comma, let's make sure that the pressed key exists. if this key exists and this key in will also bound this to key w, the key of w, then we can copy that key that we have defined, key of s a t z and x. So up, down, left, right. Then we can action the third is the delta, the till third value. So what we are doing here, we are setting the components directly and then we can break. Because for that loop, we have captured the key. One thing I forgot was this. There is one more movement that this robot does. Is the gripper movement. Is the open and close state of this gripper. And we'll also need to define the keys for our expert. So what we can do this directly. If key is pygame dot k, let's define c for close, then we can define the action equals to -1 is the inward movement, and L if keys pygame dot k will use open for, and we can just copy this, and instead of this one it is going to open the gripper. So once these things are clear, we need to get the next observation. So what we have done here, we have collected the actions. Now we need to pass this action to the environment. And then again collect back the observations. So it is going to give this next observation rewards terminated truncated in the info, because how much reward we are getting if by taking that step we want to measure it. Let's also increase this step. Now we need to also measure the, like, we'll also need to save these transition as it is happening. Right now what we have done is collect the actions and then feed it to the environment back. So let's do one thing. If we have taken these steps, and how frequently, like there is way like you can do it on every steps, but this is going to explode your data, and we can define some precision, like if it is the multiple, let's say every 5 steps, sampling frequency every 5 steps. If it happens, then, or if it is a terminated state or it is a truncated state, then we can capture the transition. So what we are going to say the observation directly as OBS, the action, and we can also say reward. And we can also, because it is going to be helpful while training the data with the current observation, what should be the next observation. So we will pass the next observation and the done state. Like by taking this observation, is it done or not? So that we will be able to know with the truncated or the terminated state. We can define. Let's also save the info. Now, and if we can save this much, and if we want exact copy, like for training the neural network, then we can use the exact value as well for the network. For now, let's only copy, try to capture this much. So the episode data dot append, we have defined an array, and we can push the transition inside that. And then once this is done, we can define the observation, the current observation to be the next observation, so that we move to the next stages, and then we can render the environment for 1, and we can increase our time by 20 steps. So this is the frame rate. Actually, for smoother control, I have made it to 20 frames per second. And now what this pipeline is, what it is going, as a human interacting with this environment, it is going to capture everything, and it's going to save everything in an episode data. But we don't know when to stop. Meaning when we are doing the rendering process, you'll see we have reached the object, but there's no way of doing that. We have achieved the desired criteria, so we'll have to write the logic for that. So we can define a flag, episode successful. Let's mark this as false, and then we can define a current distance, numpy dot linear algebra dot normalization, sorry, norm, achieved goal, minus desired. This is what we are going to measure. So if the current distance is very less, let's say 0.05, that means we are really close to the object. Then we can mark this episode successful to be true, and we can also mark the terminated to be true, and done to be true. So if, let's say, if the difference, because we are taking the norm, So this can also like our we can also do it with reward as well. So let's say our rewards is right now 0.0. Like we this is a high reward case. We then also we can mark this to be successful, terminated to be true, and done to be true. Or if it is a case of terminated or truncated, then also mark this to be true. But if it is a case of terminated, then that case let's also for now let's mark this to be successful, which means like episode completed successful, task is finished in the prior steps. Not you need to differentiate like when the episode is ended with the exceeding of time, like meaning in that time we were not able to, so we cannot like run, we cannot give an expert the whole day to capture this data, otherwise it will take complete storage of your server wherever you are running. So this is the case which handles it. So if we don't do else, then it's also fine. Now what we need to do is if it is a done and if episode is successful, then we can say successful episode as well. Like we have captured one data, success data, and then let's also capture the timestamp when it happened. Datetime dot uh, the moment that it is captured successfully, then we can format that as year, then, then date, and on the hour, it's also a month, seconds, sorry, minutes and seconds. Then we can say episode episode data dot append. We can also append some metadata if we want. For now, let's leave it. What we are interested is, let's first save in a file. So in a separate file, it will be helpful to debug like what happened. Can find the output folder slash episode, and then we can find datetime.now. Yes, topical. So with open episode file as write binary pickle.dump episode data, and if it is done, then we can break off this while loop since we get our uh, successful episode. If that is not the case, then uh, we can ask user press any key to continue to next. That is, we will prompt user to go to the next stream, and we'll just take an input so that Pygame environment is compatible with that. So now let's go pygame.time. Let's also wait for 1 second before we transition to the next step. Finally, when all of these things are done, we'll close this environment and we can pygame dot quit such that our environments are closed properly. So now let's run this finally. We can get the init environment, that function that we have defined, and then we can call our teleops collect. We need to pass the environment and the sampling frequency. If you don't pass it, it's still going to take 5. So after everything that we have done, we can run this code and it's going to show us. So I was doing some debugging and uh, I have added some debugging statement. There was one error. So hopefully now we'll run this and that error is gone. Collect data. So yeah, let's collect every 5 steps. So it's asking for seed value. So now what you can see, I am moving this robot with my, see, I have closed the, I have opened it. Now I can close the gripper and just the way we have written the code is we have to like continuously press the close button, otherwise gripper will open. We can also fix that, but for now it works, and we were able to save the expert demo here, and it was really cool doing that. Now before moving to the next part, we are going to train a BC model. What I'll suggest is you run this code and record multiple of such expert examples, a lot of examples, and then we are going to train a neural network from our dataset. It is going to do everything that we have done. So for example, it has completed in 416 step. It has collected 83 transition, and we can, let's do one thing. We'll also run it one more time. Let's keep this seed as 3443. This time it is somewhere else. So let me hide this menu. Let me also. So what we are going to do, it's not visible. Yeah, we can go here and there. Let's see, we can close this. And let's move up. Perfect. We just need to bring this to the red position. Finally, we did it. And this time it's saved with different seed value. And you can see as we are doing this, the reward is getting increased because we are getting very close to the desired position. So yeah, hopefully you will be able to replicate this same thing. I'm going to push the same code onto the GitHub so you can start doing the collection. And after that, we'll train our own PC network. Thank you.